Hello again. This is Pamela Iison from the Massachusetts Toxics Use Reduction Institute, or TURI. In Massachusetts, companies have been evaluating the technical and economic feasibility of options for reducing their use of toxic chemicals since 1990. I'm happy to share some of what we've learned in that process, as well as best practices employed by alternatives assessment practitioners from around the world. As with the rest of this training, what is presented here touches on key concepts, but does not dive too deeply into the details. We want to make sure, however, that you are on the right track. In this session, we will focus on two core components of an assessment of alternatives: technical and economic feasibility. At the end of this session, you will be able to understand the general tiers of evaluating both technical and economic feasibility. You'll know strategies for identifying essential performance and quality requirements. You'll know strategies for identifying and evaluating performance information. You'll be able to outline the types of costs to address, and you'll understand the range of cost analyses that are used. Cost and performance are generally the first elements examined when choosing alternatives to a substance of concern, often to the exclusion of health and safety considerations. While these elements are important, they may underestimate the true costs of using a substance of high concern, overestimate the costs of substitution, or impose exaggerated performance needs. In this training, we are delving into the assessment of performance and cost after assessing hazards and exposure. Yet this need not be the order of an assessment. In assessments completed as part of authorization applications under REACH, for example, the assessment process often starts with examining issues of performance and cost. And performance requirements, for example, by law or specification, may be considered at the beginning of the assessment to limit the range of options considered. There's no right or wrong order. The key is to address each component, consider trade-offs, and make decisions that move us towards the use of safer and feasible alternatives to hazardous substances of concern. Ideally, we are looking to identify options that are safer, affordable, and effective. And as this Venn diagram depicts, the space where all three elements are achieved is a small subset of the range of possibilities we face when searching for the right alternative to a chemical of concern. But that doesn't mean there aren't any options. In fact, within this seemingly small intersectional space, there really are innumerable possibilities. Your job is to find them. In session 3, we looked at the issue of safer. Now let's look at the effectiveness portion of that Venn diagram. It goes without saying that alternatives need to work in order for them to be considered suitable substitutes. But what does need to work or need to perform really mean? This is where the assessment of technical feasibility and an assessment of alternatives can get complicated. Your goal is to find an alternative that will allow you to continue to manufacture your product or operate your process in a way that supports your continual improvement and competitive advantage. When assessing technical feasibility, it is critical to evaluate and compare alternatives against specific key functional requirements. This evaluation should be conducted in a manner that is commensurate with how the facility considers any other process or product design or redesign decision. To do otherwise suggests that the evaluation is not being conducted in good faith. As a practitioner, your goal is to determine if there are safer, effective, and affordable substitutes to the use of a chemical of concern, understanding that there are significant potential benefits to identifying and implementing such a change if appropriate. Don't shortchange this effort by being more restrictive with your assessment. If your product can function well within a specific range of viscosities, for instance, you do yourself a disservice if you narrow that range when you consider alternatives. The depth of technical performance assessment needed will vary depending on who is conducting the assessment. Assessments are data dependent, and the data available will be different depending on whether you are an enterprise needing an alternative product to replace one that contains a chemical of concern, an enterprise that manufactures specific products who is examining alternatives to a chemical of concern in the production process, such as a processing aid that does not get incorporated into the final product or in a final formulated product, or a government authority or an NGO seeking to understand if technically feasible alternatives are available or if certain performance requirements are actually necessary. Another consideration affecting the type of technical feasibility assessment you will conduct is the degree to which the alternative is currently incorporated into readily available and tested products already on the market. The availability of pertinent performance or technical data associated with a potential alternative will also influence the type of technical feasibility assessment you will conduct. Exhaustive technical assessments are not needed or useful in every situation, but may be required in situations where certifications or performance requirements are necessary. Considering the varied approaches needed given different entities conducting the assessment and for different purposes, it's helpful to structure assessment options along 3 tiers with increasing levels of complexity. Each level builds on the one before it. Level 1 is the basic assessment. Here you will be using publicly available performance data to assess the feasibility of options. Level 2 is the expanded assessment. In this tier, you will be using publicly available performance data to evaluate options against specific performance criteria. Level 3 is when experimentation and testing is necessary. In this tier, you will be using in-house or partnering test facilities to evaluate alternatives against your performance criteria. We'll dive into more detail in later slides. Regardless of the assessment level you will engage in, you will always begin with the scoping stage. In session 1, we discussed how a key step in determining the scope of your assessment of alternatives is specifying the function provided by the chemical of concern and therefore the function needed to be replaced. Recall from the scoping module that the function is the service or action that a chemical broadly provides. Solvency, corrosion resistance, wettability, flame retardancy, etc. Session 1 also highlighted the need to define specific performance requirements at the scoping stage to help identify viable alternatives and collect preliminary information. At the scoping stage, we also highlight the value of questioning why the substance of concern is being used and whether that function is indeed necessary. Be sure to revisit these key elements of your scope when you begin your technical feasibility evaluation. In evaluating the potential performance of alternatives, it is important to be clear about what performance attributes are critical for a viable alternative. In searching for answers to these questions, you should especially look for examples of successful use of the safer alternative by other companies in similar businesses and similar ranges of applications. So here are some questions that you can seek to answer. Will use of this safer alternative allow me to meet the quality demands of the market? Will this product provide equal or better operational efficiency and productivity? Will using this alternative adequately ensure that my product will be durable or any other critical factor in your performance assessment? Will the use of this alternative require me to provide substantial retraining of my workforce, and will my employees be up to that challenge? Performance requirements are case-specific and depend on the function needed as well as the technological process, application, or product involved. It is important to identify performance requirements that can be either qualitatively or quantitatively measured. Consider performance requirements dictated by users and those dictated by quality. User requirements can include chemical properties, for instance, a solvent and the need to dissolve specific types of resins in a paint stripping product. Physical properties, for example, a printing ink that needs to transmit a specific color, or mechanical properties. For example, a material substrate may need to provide specific tensile strength or fracture toughness. Performance quality measures are somewhat unique to the specific application. These can include requirements such as reliability, longevity, durability, ease of use, time required to meet the specific function, etc. Industry standards, such as those developed by ASTM International, ANSI, ISO, etc., may define performance standards for specific uses or applications. You may also need to consider user specifications, for example, the specifications delineated for military applications. Engaging stakeholders, workers, product designers, and production engineers, for instance, can help you identify these performance quality parameters. You may also need to consult with suppliers and customers, not only to identify the critical parameters for evaluation, but also to gather information about the performance of alternatives under consideration. When identifying critical performance requirements, focus your efforts on those that are necessary to achieve the specific function you're replacing. For instance, the level of corrosion resistance that can be achieved by an alternative to hexavalent chromium in electroplating applications. While this is clearly the primary function of the substance of concern, hexavalent chromium, other functional attributes that it provides, such as wear resistance or hardness, may have more flexible parameters to be met. Remember that setting performance requirements that are too specific may narrow the scope so much that alternatives may be difficult to find. Here are a few more aspects of performance that you should be thinking about as you enter into the technical feasibility assessment stage. What is acceptable performance when addressing technical feasibility? Can you define this in a way that sets you up for success in finding technically feasible substitutes? What are acceptable tolerances for performance, and who decides this? Working with stakeholders and customers will help you in understanding how much flexibility you may have with certain technical characteristics. Could the different qualities you are looking to replace be produced by different combinations of alternative substances or technologies? Don't limit yourself to only drop-in replacements. Remember that process modifications upstream of the point where the substance of concern is used may eliminate the need for the function it provides. Consider the use of toxic degreasing solvents. Modifying upstream processes may allow you to eliminate the contaminants that had resulted in the need to provide that level of surface cleaning. Does implementing the alternative create additional hazards or trade-offs in order to achieve adequate performance? Okay, let's look at the first tier of technical feasibility assessment, level 1, the basic assessment. At this level, you want to first identify critical use and performance or quality requirements. Remember, you should already have this information from the work you did at the scoping phase of your assessment. Remember to use publicly available data sources such as academic literature, information from vendors or suppliers, government reports, etc. Contacting and talking with representatives from manufacturers, trade associations, and customers who use the chemical or its alternatives is often the best way to obtain this information. Use your performance requirements to inform your line of questioning. Consider creating a matrix to compare alternatives based on the following questions. Has the alternative already been identified as favorable with respect to critical performance criteria? Is it being used for the same or similar function and application? This is a key question that, depending on your goals, may be enough to move forward with your assessment if the answer is yes. Is the alternative chemical or technology used in similar products or processes available on the market? If yes, the alternative may qualify as feasible. Has the alternative been tested and found to match the performance achieved by the chemical of concern? If not, can the process or product be modified to accommodate the alternative and improve its performance? Or is the difference in performance critical for your given use or application? And has the alternative been identified by expert sources as unfavorable? How relevant are their results? Is their application or use of the alternative identical to your use of the substance of concern? Depending on what your level 1 assessment was able to reveal, perhaps that's enough for your needs. If not, you will want to pursue a level 2 expanded assessment. At this level, you need to identify appropriate experts, process engineers or scientists like chemists, material scientists, etc., to help you gather the necessary information. Use your functional use and performance or quality requirements identified and establish a performance scale for each. The scale can be quantitative or qualitative depending on the measure. You should use relevant performance standards or specifications, including industry accepted standards or customer specifications in developing your scale. Remember, it is important to determine what are acceptable tolerances related to each performance measure. What level of performance is good enough? Use the results of how the chemical of concern performs as the baseline for your comparison. A more exhaustive search for pertinent information is necessary at this level of technical feasibility assessment. Collect information from the literature, suppliers, and expert consultation, and plot performance results in a comparative matrix. For some, especially those that are manufacturing products or who have processes that are dependent on the substance of concern, level 3 performance testing of alternatives may be essential. At this level, you need to engage with appropriate experts, such as process engineers or scientists like chemists or materials scientists, to help you design the appropriate tests and to identify the variables with which to experiment. You will need testing facilities either in-house at a contract facility or through an academic institution partnership. Use your functional use and performance or quality requirements identified and establish a performance scale for each. The scale can be quantitative or qualitative depending on the measure. Use relevant performance standards or specifications. Determine what are acceptable tolerances related to each performance measure and conduct the relevant performance tests. Working with a coalition of similar companies in this research may be helpful in these cases. Next, we'll be hearing from one practitioner, Dr. Gregory Morose, Research Program Manager at the Massachusetts Toxics Use Reduction Institute, who has employed many of these steps to determine the technical feasibility of safer alternatives. In the next slide, we'll hear from Dr. Gregory Morose, who's the research manager at the Massachusetts Toxics Use Reduction Institute. He'll discuss what he's learned about adequately assessing the performance of possible alternatives to substances of concern to develop options that can be adopted by various user types. You can also access an article written by Greg and his colleagues that outlines their approach for lead-free soldering in electronics in the readings.
Hi, my name is Greg Morose, and I am a research professor at the University of Massachusetts Lowell, and also a research manager at the Toxic Use Reduction Institute. And I've been asked to speak to you today about some lessons learned and some rules of thumb that we've come across doing performance evaluations as part of comprehensive alternatives assessments to replace highly toxic chemicals for various applications. So some rules of thumb to consider when doing performance evaluations are: first, you really need to understand what function that the target toxic chemical is playing within your application. So there are many different properties of these toxic chemicals, so you want to make sure that you're targeting the specific property or properties that are performing the basic function that you're attacking here. So you really want to make sure you have a clear understanding of that. And once you do, and you have defined the application that you're looking for, you really need to pull together the thought leaders that real deep understanding of this application. So typically it's not just one company, you've got multiple companies in an industry. You want to get the thought leaders from each of those companies and pull them together. And the way to identify these, sometimes it's a little tricky, but one method is to first find out what type of industry standards or specifications are used in the industry for this application, and then find out who authored those specifications and who's on the committees of those specifications. And usually those are the industry experts that have gotten together to put those specifications together. So it's really key to contact those experts and get them together so that you can start to define what the critical parameters are to put together both design a test vehicle and to design test protocols to do the testing that will accomplish what you need. So when you get these experts together, what you need to do is design a test vehicle or a test platform in which the testing will be conducted. And also you need to put together the test protocols on how you're going to do the testing with that test vehicle. So test vehicle, you want it to be as comprehensive as possible. So as an example, this is a test vehicle that we came up with for where we're looking at lead-free solder for the electronics industry. So this is an actual circuit board. So we tried to make it as realistic as possible. And also, as you can see, there are many different types of components on the board. So we tried to have this single test vehicle encompass through-hole components as well as surface mount components. And then many different types of geometry. So you can see there's connectors here, there are ball grid arrays, there are just a wide variety of different types of components, both large and small, so you have different thermal masses. So this is an example of putting together a test vehicle with a number of different varieties of applications that you'll see out in the field and accomplish it with one test plan. So after you design the test vehicle, you need to put together a test plan. So how are we actually going to conduct the test with this test vehicle? And again, you really need input from all the different thought leaders within the industry to pull this off. So some of the things that you have to think about is when we conduct the tests, is it a demanding enough test for this application? Because if the test is too easy, then if alternatives pass, then they could be challenges saying, well, that was a very easy test, anything could have passed that. So we try to make the test as challenging as possible, as rigorous as possible, so that if it is passed, then there is a high degree of confidence that the target chemical can be replaced and the alternatives have acceptable performance. So with the test protocols, you also need to determine if is any statistical significance required. So do you need to do replicates? Do you need to do design of experiments or analysis of variance? So what type of statistical tools and significance are needed for your results so that there is confidence that you're meeting your objectives? So here is an example of a test vehicle that was designed for trying to find a replacement for lead and solder for the electronics industry. And what we're trying to demonstrate here is that this single test vehicle encompassed a wide range of different component types so that we could validate that the lead-free solders would work with a variety of components. So on this single board, we have through-hole components, we have surface mount components, we have connectors, we've got ball grid arrays, we've got a wide variety of component sizes and shapes and geometries and different component finishes. So with one single test vehicle, we're able to accomplish testing for all these different types. So here is an example of, there was an industry standard for removing paint coatings from the substrate. So with our project trying to find a safer alternative to methylene chloride-based paint strippers, we needed to either use that specification or even enhance it. And in our case, we thought it made much more sense to enhance it to make it more robust, because the specification that was used in the industry just required 3 layers of top coat. And the feeling with the thought leaders in that industry was that it was not a very demanding test. So we took that industry standard specification and we modified it. So what we did was we required a primer layer to be added to the substrate, and we increased the top coat layers from 3 layers to 4 layers. And we also tried to make better adherence between the coating layers. So we had sanding and cleaning steps between each layer application. And finally, we thermally aged the test vehicle afterwards to simulate approximately 1 year of aging. So that made it even more demanding. So by making those changes to the industry specification, we thought we had a much more robust and challenging specification and test protocol. So here is another example of a test vehicle. In this case, this was for trying to replace hex chrome used for corrosion protection in various coating layers for military and defense applications. So once again, we tried to find the most demanding application and test to that demanding application. But we recognize that there is a whole spectrum of different requirements. So we did the corrosion testing on this in the salt fog chamber, and we ran the test out all the way to the most demanding application. But we did have some alternatives that didn't make it all the way to the end, but we still found that they were viable solutions for some of the less mission critical applications on, say, a military aircraft. So say in the cabin of an aircraft, the interior, it's not seeing as much weather and elements, so therefore the corrosion requirements are not quite as high, as opposed to an external component such as the landing gear, which would be considered mission critical and would have the most demanding corrosion resistance application. So so there's a whole spectrum. So you want your test protocol to encompass the whole spectrum of applications and requirements. So some of the alternatives might be work for the less mission critical, and some of them might work all the way up to the fully mission critical application. So in summary, for all those 3 different applications that we just talked about, the methylene chloride on the paint strippers, the lead solder in electronics, and also the hex chrome in the various coatings and military applications, we were able to find alternatives that met the most demanding applications for each one of those scenarios. So it can be done. We've done it, and we've got the papers and publications to show the results. And it's just a matter of getting the experts together and making sure that you are very mindful and when you put together the test vehicle design and the test protocols, so that you encompass all the different requirements.
Even for drop-in replacements, some process changes may be needed. Technical feasibility should not be discounted on the basis that an alternative requires process changes or product reformulation, but be aware that investments in equipment, infrastructure, and worker training may be needed to make the alternative work effectively. Additional efforts like obtaining customer approvals or certifications, conducting research and testing, or identifying legal requirements or restrictions may be needed depending on the level and type of process changes involved. Indeed, some process changes may result in an overall benefit to your facility, including greater productivity or improved working environment. Remember that the best alternative may involve a far different approach than finding an alternative chemical. It may require a redesigned process or even a more systematic change. Here is an example of a wood furniture manufacturer that turned to a water-based adhesive, requiring a significantly different process and new equipment, rather than simply replacing methylene chloride with another organic solvent. This major change required performance testing to demonstrate efficacy. What they discovered was that stronger bonding performance was achieved with the water-based adhesive, In addition, they were able to increase overall productivity by reducing drying time through the addition of heat in the process. Whether you conducted a level 1, level 2, or level 3 assessment, make sure that the results of your technical feasibility evaluation are plotted in a clear comparative format. This can be tabular or graphical. Use the format that is most commensurate with other methods used at your facility to evaluate options. In addition to performance criteria, consider the following when addressing the question of technical feasibility: consideration of process and formulation changes and supply chain changes. Despite your best efforts, you may still find that a safer alternative simply isn't technically feasible. There can be a variety of reasons why this may be, many of which are shown here. Be careful when making the determination that an alternative is not technically feasible. Remember that other factors may be able to be modified to make what had been infeasible now feasible. If you are finding that there are currently no technically feasible options, you are called to be even more creative, to dig deeper and develop a plan of action and priorities. Use the resources and results from your technical feasibility assessment to brainstorm what is needed to develop the most promising alternatives sufficiently to achieve technical feasibility, and justify the time and resources needed to do so, including details of necessary research and development, the required timescales, and cost. Remember, assessments of alternatives is action-oriented. Many times, technical feasibility is a challenge, but the answer is not to simply keep using the same toxic chemical of concern, but rather to prioritize the research and development, including developing research partners needed to discover suitable alternatives in the near future. In the meantime, the results of your assessment of alternatives thus far may help you identify how to further reduce exposure, improve working conditions, or minimize waste, for example. Keep the goal of a safer, effective, and affordable alternative in mind. As we like to do, we offer a few questions for further reflection. Think about what technical feasibility challenges you may be facing in your organization. Would one assessment level be more achievable? How might you overcome some of the barriers you anticipate encountering? Key concepts to remember when conducting a technical feasibility analysis of a project include the following. Understanding the function currently provided by the substance of concern is important. Equally important is being willing to take a step back and look at whether that function is essential to the process or product, and if other process or product changes might allow you to forego that particular function. There are a multitude of variables that make your process or product unique. Trying to mimic all elements of your current system can make for an overwhelming or worse, impossible evaluation hurdle. Rather, identify those key performance indicators that impact acceptance of your product or your ability to implement process changes. Focusing on these key elements will facilitate a clear comparison between your current system and the alternative being considered. The level of technical feasibility evaluation you choose to do depends on who is conducting the evaluation and what the driver for completing the assessment is. Be sure to clarify these considerations and gather sufficient information to allow you to accomplish your goals. Knowing who has important information about performance and technical feasibility and engaging them in the process in an appropriate way will facilitate your assessment and help assure that you haven't neglected to consider key indicators. As always, apply the same metrics your facility would apply to any other process or product redesign project. Doing so demonstrates your good faith effort to find an effective alternative to your use of the substance of concern. Once you've identified a safer alternative that is technically feasible, it's time to look at the final element of an ideal alternative to a chemical of concern, namely one that is also affordable. It is appropriate to determine if a potential substitute is economically feasible as the last step, so that possible options are not ruled out too early in the process. If an alternative will have a broader impact on quality, community goodwill, market share, process throughput, or other metrics, the financial implications of adopting the substitute may have less weight in the final decision. At this stage, therefore, we are focusing on gathering sufficient information to help support a decision to adopt the alternative or to rule out any options that are clearly infeasible. Conclusions on technical and economic feasibility of an alternative substance or technology have to be seen in a logical hierarchy. Technical feasibility is a necessary condition for an alternative to be suitable, whilst economic feasibility is a necessary and sufficient condition. In other words, an alternative can be technically feasible but economically infeasible, whereas it is impossible for an alternative to be considered technically infeasible but economically feasible, for it would be impossible to find a buyer for the resulting product. Similar to assessing technical feasibility, the level of an economic assessment needed for informing alternative selection will vary based on who is conducting the assessment and for what reason. Economic feasibility assessments are performed on a variety of levels, ranging from quick market assessments to detailed industry-wide socioeconomic assessments that are being driven in part by regulatory alternatives assessment requirements. Various cost considerations are important in substitution decisions. If alternatives are not cost competitive, they are unlikely to be considered viable by company decision makers. The goal of an economic feasibility assessment of alternatives is therefore to understand and compare costs relative to the substance of concern that you are seeking to replace. In conducting an economic feasibility evaluation, it is important to understand that cost comparisons are snapshots in time. They may also be of limited relevance for emerging technologies, since learning curves, economies of scale, and other factors can reduce costs over time. The overall costs of implementing a substitution or process change are related to many things, such as the higher price of different production inputs, costs associated with generating more scrap, investment in new equipment, research and development costs, etc. Identifying the relevant cost factors to focus your assessment on is key. Some of the costs associated with implementing an alternative are fixed, such as the costs associated with building out a new production wing to accommodate the alternative process, while others are variable, such as changes in energy consumption associated with a production line. Variable costs are often dependent on the quantity of product produced. When evaluating options, there are many immediate and long-term cost implications. Therefore, understanding the likely usable lifetime of the options you are considering will help you in better assessing the overall savings potential associated with this change. Use your company's standard accounting practices to understand how these long-term costs and savings impact the feasibility of the project. Numerous costs and savings will be relevant in your evaluation, but not all costs need to be studied to the same degree, depending on the complexity of the evaluation you're embarking upon. Direct and hidden costs and savings should be identified as you initiate your assessment. A good place to start is with the costs posed by your use of the substance of concern. We'll talk about some specific costs and savings to consider in the next slide. The availability and supply of a substitute you are considering will greatly influence your assessment of a substitute's economic feasibility. Clearly, if the alternative is still emerging on the marketplace or even still only at the R&D stage, it is unlikely to represent a reasonable option at this time, and the costs associated with using it will likely far exceed those for an established option with an established supply chain. When considering a process or product substitution or redesign, pay attention to the potential impact on regulatory requirements, as well as the potential for future chemical restrictions that may be posed by government authorities or your customers. In addition, consider the benefits associated with removing substances of concern from your process or product. Liabilities from environmental or worker health impacts may be avoided or significantly reduced, and there is a savings associated with this. Not all costs are easily quantified. Many hidden costs and savings can be realized when making a change. We'll look at a few in the next slides. Finally, a company's ability to adopt a change is often limited by financial factors such as the availability of revenue to pay for the costs of implementing change. Here is a list of various direct and hidden costs that may be relevant to your evaluation. As noted previously, not all costs are relevant to your assessment, and not all costs are easily quantified. As the practitioner, it's up to you to gather sufficient information about relevant costs and savings to allow you to make the case for implementing a safer and effective alternative to your use of a substance of concern. Looking more closely at those harder to quantify costs, we see a variety of economic impacts that could result with the change you are considering. As you embark on your economic feasibility evaluation, don't forget to consider these issues and determine an appropriate way to provide a meaningful comparison of the costs and savings that could be realized. This will help you in making the case for a change that, at first blush, might not appear to be economically feasible. I want to stress that it is so important at this stage to resist the urge to eliminate an option too quickly. Many of the cost factors you will be gathering information on will change with time, and looking more fully into the long-term implications of making a change can also influence your company's decision to adopt the alternative. Here are a few essential elements to keep in mind as you conduct an economic feasibility assessment. The cost of the alternative needs to be considered in comparison to the current and potential future cost associated with using the substance you are looking to replace. The availability of the substance being considered may change with time, which will likely affect the cost to use it. A substance currently under development or available only through one supplier may become more affordable as demand for it increases and competition to supply it increases. Finally, as I've said before, it is critically important that you use the accounting metrics and methods that the company would use in making any other financial decision. Understanding what those investment criteria are and being careful to not apply more restrictive targets than would otherwise be used is a sign of a good faith effort in determining the economic feasibility of an alternative. Similar to assessing technical feasibility, it's helpful to structure tiers of assessment options with increasing levels of complexity. What level you choose to do reflects the role of the entity conducting the assessment and the context surrounding the assessment. For instance, a company considering a specific potentially restricted substitute for its substance of concern in a discrete process or for a specific product may be satisfied with a basic cost assessment since drivers for change are external. If the assessment of alternatives will be used to guide proactive shifts in business operations or investments of the facility using the substance of concern in response to a long-term strategic effort, an in-depth evaluation may be preferred. Each tier builds on the one before it. Level 1 is the basic cost assessment, which allows you to address current use and market availability of the alternative in the use or application of interest. Level 2 is the expanded cost assessment that addresses any difference in direct costs, such as manufacturing costs, and indirect costs, such as regulatory compliance costs, emission controls, liability costs, and considers whether there is enough supply on the market to meet demand. Level 3 is the external cost assessment. At this level, a socioeconomic analysis or cost-benefit analysis is conducted to address costs related to environmental and human health impacts, costs incurred by regulatory authorities, or other life cycle cost impacts, such as those associated with resource extraction, public perception, or product labeling. These types of analyses are typically required by regulatory authorities. For instance, the California Department of Toxic Substance Control requires a socioeconomic analysis, or SEA, for alternatives analyses conducted under its Safer Consumer Products regulation. The SEA is one route for authorization applications under REACH, taking into account the health and environmental benefits or costs of substituting a substance of concern. These types of cost-benefit analyses are often required to justify new regulatory actions. This assessment level does not require sophisticated economic or accounting experience and focuses on using vendor information and market research to address these questions. Is the alternative commercially for sale? Is the alternative already available on the market for the application or use of interest? Can we obtain the alternative at the levels of supply needed? For some entities, if the answer is yes to these questions, this may be sufficient to justify that the alternative is economically feasible. At the most basic level, the mere presence of a product on the market means it is economically viable. It's available in the use or application of interest at the supply needed, and it's cost effective for some sectors. However, this may not be detailed enough information if the focus of the assessment is an alternative being considered in a formulated product or needed as a process chemistry in a manufacturing process. An expanded cost assessment may then be needed. A simple expanded cost assessment may be just a comparison of alternatives on a per unit price basis, considering whether more or less of the input is needed. Level 2 examines more specific questions related to supply of the alternative and delves into comparison of costs. This is an example of full cost accounting that has been used in pollution prevention programs. At this level, economic and/or business accounting experience is needed. Consider the current and potential future supply of the alternative substance or process and answer these questions. Is the alternative being produced in sufficient quantity to meet demand if the alternative is used in place of the substance of concern? If the demand increased, could it be produced in sufficient quantities and by multiple suppliers, ensuring a constant supply? Consider the various costs and what the impact of implementing the alternative would be to direct and indirect expenses. As mentioned previously, direct costs typically include manufacturing costs, such as costs associated with chemical purchases, capital or equipment costs, and chemical or material costs, including additional processing chemicals if needed. Other direct costs include those associated with transition and training, transportation, maintenance and storage, end of life or disposal, energy consumption, and employment and labor productivity. Indirect costs or non-direct manufacturing costs include expenses associated with regulatory compliance, such as industrial hygiene, engineering controls and equipment, emission controls, etc., and liability costs, such as costs associated with spills, fires, explosions, or worker compensation claims. The assessment itself can be based on enumerating costs and comparing whether there is net savings, net costs, or no change in costs associated with the use of the alternative versus the chemical of concern. A calculation of payback period, that is, how much time until the investment is recouped, could be used. However, more sophisticated accounting measures like determining the return on investment or the net present value of implementing an alternative will likely give you a better understanding of the long-term implications of adopting the alternative. These metrics also help in making a more informed decision whether to adopt or not. Remember that some cost measures are difficult to enumerate. For qualitative cost elements, devising a comparative method that allows you to depict the likely financial impact if an alternative is adopted can be used instead. Answering one of the key economic feasibility questions, is it cost effective, may not be as straightforward as comparing total costs and savings. There are additional questions to layer into this economic assessment process to better understand the viability of a given substitute. These questions can help guide assessors in answering whether the alternative is a suitable replacement from a cost perspective or whether it is prohibitively expensive. It is important to consider not just costs, but benefits associated with adopting the alternative. Often the benefits may accrue longer in the future than the costs. Questions to consider at this point include, is the cost of the alternative close to that of the current chemical? Making this determination based on, for instance, likely cost per unit of product manufactured or production rate can help to provide a better apples to apples assessment. Considering additional factors such as durability, that is, reducing repurchasing costs, or increased productivity may also affect your assessment of the cost competitiveness of the alternative. Can changes be made to your product or process design so that the overall cost of using the alternative is less than the current comparable material containing the chemical of concern? Is it possible to redesign the product or its application so that less of the possible alternative chemical is needed? Can changes be made to add value to the product? For example, although the redesigned product containing the alternative may be less cost effective, does it open new markets and avenues for expansion? If demand for the alternative increased, could the price be reduced? Will the alternative have benefits in terms of improved compliance, better image in the marketplace, etc.? What are the opportunity costs of not adopting the alternative in terms of lost markets, reputation, etc.? And can any actions be taken to eliminate or minimize the cost and availability impacts? Examples include purchasing contracts, setting volume and price for defined periods, recycling programs, product stewardship programs, and use minimization practices. Remember the furniture manufacturing example we discussed previously? There were positive technical outcomes associated with implementing the change from a methylene chloride-based adhesive to a water-based adhesive system. But if they had looked only at the cost of the adhesive itself, they may not have made the decision to implement. Fortunately, they considered more cost factors in adopting water-based adhesive process as a safer alternative. While the water-based adhesive costs more per gallon than the methylene chloride-based adhesive, the higher solids content of the water-based adhesive reduced the volume of adhesive needed, which resulted in an overall savings for the new process. In addition, the cost of energy required to heat the furniture to fully dry the wood using the new system actually decreased the overall drying time, resulting in an increase in production throughput. More throughput meant more furniture available for sale. This company found that the operational savings realized by this new system paid for capital costs quickly, providing greater long-term profitability. To be clear, the motivating factor for change in this example was the increased regulatory requirements for continued use of methylene chloride. But prompted by the regulations, the company looked for innovations that would meet the reduced hazard objective of the revised regulations, as well as meeting their business profitability objectives, and they succeeded. Here is an example of a healthcare center looking to reduce respiratory irritation, asthma attacks, and absenteeism its cleaning and maintenance staff experienced during semi-annual stripping and re-waxing of its vinyl flooring. When the time came for replacing the old vinyl flooring, the center considered two options. One, install new vinyl flooring and search for somewhat less hazardous stripping and waxing products, or two, replace the vinyl flooring with rubberized or polymeric flooring that required no waxing or stripping. Let's look at the evaluation. The initial cost of the vinyl flooring was only 1/3 as much as the other flooring products evaluated. But by eliminating twice annual stripping and re-waxing, floor maintenance costs were dramatically reduced. Therefore, over the 25-year estimated life of the flooring, the non-vinyl flooring was considerably less expensive. Unfortunately, from the perspective of the center's financial managers, the expected payback period of 5 years was just too long. Considering the time value of the savings realized over the life of the new flooring would have been helpful in making a different decision. Other factors weighing in favor of the initial capital expense included the fact that this system change would completely eliminate the use of hazardous cleaning chemicals, as well as the associated health impacts of those chemicals on its employees. Historically, when substances were released into the air, water, or soil through production, use, or disposal phases of a product's life cycle, society paid for the impact costs, not the polluters. The Level 3 assessment builds on the evaluation of costs to the business and also evaluates costs related to public health and environmental impacts, as well as costs associated with government agencies and nonprofit organizations' resources to manage waste or to oversee environmental cleanup that may result from releases. Socioeconomic analysis, life cycle costing, and/or cost-benefit analysis experience is needed to perform a Level 3 assessment. These types of analyses are required in California and in the SEA pathway for REACH authorization. It is beyond this training to delve into this topic, but please see the supporting resources provided for more information.
Hello. I'm Ray Lazat, Director of Sustainability at the Secure Power Division of Schneider Electric. Like most of our companies, Schneider Electric's primary purpose is to make money. That means anything that is proposed to improve the sustainability of one of our offers is evaluated from a cost perspective. Each of us who do alternative assessments have to understand the process that is used by our company to perform these economic feasibility assessments. At Schneider Electric, the size and the scale of the project defines which economic feasibility assessment will be performed. Simple, low-value projects require evaluation of only direct costs. Direct costs are those that can be specifically tied to the use of a chemical or a technology. As a project gets larger and more costly, other factors, such as indirect costs, are added to the assessment. Indirect costs go beyond the use of the chemical and the technology, but they address also the cost impacts of that chemical or that technology on the overall company. This term, total cost of ownership, is used to describe the sum of direct and indirect costs. Because of the nature of sustainability projects that utilize alternative assessments, economic feasibility is typically based on the total cost of ownership. In my experience, the direct costs are easy to define, but the challenge is to quantify the indirect costs. Many of these indirect costs aren't really costs at all. They're avoided costs. For example, they could be the cost savings associated with avoiding the cost of having to meet a regulation, or the impact to the company's healthcare costs because of the use of a toxic chemical. Calculating realistic costs, avoided costs, can be a challenge. I remember reviewing my first economic feasibility assessment with a VP of finance. I put lots of work into each value in the assessment and was quite proud of it. The VP reviewed it, smiled, and said something that I'm going to pass along to you now. He said, avoided cost of future regulations is like justifying the cost savings of bicycling to work. If you base the assessment on the cost of driving, then you will get a certain amount of avoided costs. However, if you instead base it on the cost of taking a taxi to work, you'll get an even greater cost savings. So is your assessment based on avoided cost of car or taxi? I've really taken this to heart because it really underscores the challenge that we have in our economic feasibility assessments. I find it so important that when I'm doing mine, you can often hear me muttering in the background, car, taxi, Uber, space shuttle, or something like that. This issue becomes even more important when the assessment extends beyond the company to the cost impacts experienced by your customer, because they purchased your product and they have their own total cost of ownership assessment to do. In this case, showing your customer how your product helps them reduce their cost of ownership is a way to market your products to them. At Schneider Electric, we utilize online economic feasibility generators, which we call trade-off tools, to help our customers calculate the impact of purchasing our products. This issue becomes even more important when the assessment extends beyond the company to the cost impacts experienced by your customers because they purchased your product and have to do their own total cost of ownership assessment. In this case, showing customers how your products help them avoid cost is a way for you to market your products to them. At Schneider Electric, we utilize online economic feasibility generators, which we call trade-off tools, to help customers calculate the impact of purchasing our products. For example, one of these tools allows a customer to determine the most economically feasible battery technology to use in their data centers. Their choices would be conventional lead-acid technology or the new lithium-ion battery technology. But rather than having this tool be based on my assumptions of what are the avoided costs, the tool allows the customer to input their own assumptions, such as the cost of their electricity, where in the world they're located, the size of their data center, how many years their data center is going to be in service, what is the backup time of the required for the uninterruptible power supplies, the replacement period for the batteries. By them putting in these assumptions, it generates a curve that they can use to assess which option has the lowest cost of ownership. So you can see here, based on what I've just randomly put in, the blue line shows the total cost of ownership of the lead acid, whereas the green line shows the total cost of ownership of the lithium ion. Because of the upfront costs associated with the lithium system, they cost more, they are flammable, so they cost more to transport to the customer. The upfront costs of the lithium ion system is much greater than the lead acid system. But when you start looking at other costs, such as the maintenance cost, the cost of space. The lithium-ion systems are just much smaller. The energy use of the system, and then the cost of maintaining the system. These are all costs where the lithium-ion system avoids the costs that would be incurred if you're using the conventional battery, lead-acid battery system. And so a customer can look at this, and by putting in their own assumptions, they can essentially determine their cost of ownership and determine which option is appropriate to them. So this would be a method that we use to have a conversation with our customers and help them through this total cost of ownership discussion so that they can understand that it's good and proper for them to purchase our systems.
Take a moment to reflect on examples where, in your experience, the price of a substance of concern was acceptable for use in a product, but resulted in an extremely high cost to society. These societal costs are difficult to quantify, but can impact your decisions. Guidance on the socioeconomic analysis required under REACH authorization helps to illuminate this point. Key concepts to remember when conducting an economic feasibility analysis of a project include the following. Be sure to gather sufficient information for the level of assessment you will be conducting. Remember that this includes easily quantifiable factors as well as hidden, hard to monetize factors. It is important to employ the accounting methods normally used at your facility for capital investment decisions. This demonstrates a good faith effort to reasonably compare the possible alternative to the use of the substance of concern and also helps in making the case for implementation. It is important to not rule out possibilities too early based on initial cost factors you may have gathered. Considering the long-term impacts of change and the many hidden benefits and costs associated with implementing the alternative will help you in fully realizing the potential benefit to your company. And remember your goal to find a safer alternative that is both effective and affordable.